when we multiplied that, what happened? Anyone remember? Stuff canceled out. So we did 2x times 2x and got 4x squared. Then we got minus 6x plus 6x and minus 9. So our middle term added up to 0, and we had just 4x squared minus 9. Well, what we're going to learn today is how to do this particular kind backwards. So we're going to start off with a binomial, and we're going to factor it to go backwards into two binomials. So one of the things we need to look at is what's special about 4x squared and 9. Think about something that they both are. There's a type of number that both of those are. Think of something. Do you know?
A prime.
They're not prime, but you're on the right track. They're one of those kind of special types where there's not many members, but they both are it. Chase? Of? That's the word. What'd you just say? They're perfect squares. 4 is 2 times 2. 3 is 9 times 9. X squared is x times x. So if you'll notice, like, how did we get 4x squared? It was because these were the same. So we got a perfect square. How did we get 9? Because the last two were the same. That's how we got a perfect square. Okay? So the pattern that we're learning today is called difference of two squares, meaning you have to have perfect squares in order to use it. So one of the first things you're going to look for is, are your numbers perfect squares? So do you guys remember what numbers are perfect squares? We have 1, 4, 9. What's the next one? 16, 25, 36, 81. What's 11? 12? 13? 169. 14? 196. 15? 225. Okay, that's good enough. So we're going to be looking for those kind of key numbers, the perfect squares. How to know if a letter is a perfect square? The exponent has to be even. So if your exponent is even, it's a perfect square. Okay? So the pattern, when you do have two perfect squares, they have to be subtracted. This doesn't work if they're being added. So that's why it's called difference. Difference is another word for subtraction. So it has to be two perfect squares being subtracted. When you have two perfect squares being subtracted, the pattern for factoring is you take the square root of the first one. So the square root of a squared is a. You take the square root of the last term, so square root of b squared is b. You put a plus sign in one and a minus sign in the other. You have factored this. Okay? But again, this only works if we have a binomial that's two perfect squares being subtracted. It will not work any other time. Okay? And I will say this, on your homework, we did throw in a couple that weren't perfect to see if you could make sure you go through that checklist. They have to be perfect squares. They have to be subtracted in order for this to work. So this first example here, v squared minus 100. Is v squared a perfect square? Yes. Is 100 a perfect square? Yes. So and are they being subtracted? Yes. Okay, so I'm going to put my two parentheses. What's the square root of v squared? V. What's the square root of 100? 10. Put a plus in one parentheses, a minus in the other. Yes, sir?
No matter which way you was to the...
Nope. As long as one's plus and one's minus, that's all that matters. Okay, and then again, to check it, if you wanted to check your answer, So to check it, we just double distribute. Put it back together and make sure it comes out to what we started with. So v squared plus 10v minus 10v minus 100, we end up with what we started. Okay, so you can always check. In fact, I encourage you to check, because that's how you're going to catch it if you made a mistake somewhere. Okay? What about the middle one? X squared minus 16y squared. So start with the questions. Are these perfect squares? Are they being subtracted? Yes. So then we write our double parentheses. What's the square root of x squared? What's the square root of 16y squared? 4y. Put a plus and a minus. Again, you can always check it. By multiplying it back together. So we'd have plus 4x times y minus 4x times y plus 16y squared. Those add up to 0, giving us what we started with. Whoa, that's a minus 16y squared, not a plus. Okay, what about this third one over here? 81r to the second minus 1. Are both numbers, or both monomials, perfect squares? What's the square root of 81?
9.
What's the square root of r squared? What's the square root of 1? Good. Okay, so then we would have 9r plus 1, 9r minus 1. And again, you can check it by double distributing. Plus 9r minus 9r minus 1. Those add up to 0. We got what we started with. Okay, any questions so far? Okay, we got 3 more. So if we look at the 9n squared minus 400m squared, is 9n squared perfect? Is 400m squared perfect? What's the square root of 400? 20, good. Okay, so, and they're being subtracted, so that means we can take the square root of 9n squared. What would that be? 3n. And then the square root of 400 m squared would be 20m, and we want, it's really common that we forget the letter if there's a second letter, so make sure you don't forget to put the letter with the 20, because on the test I see that way too much and I hate having to mark off a point for that. And then we put a plus sign in one, a minus sign in the other. And again, you can always check it. Multiply it back together. And you get these to, the middle term adds up to 0, and you're back with what you started. Okay, what about this next one? Are those both perfect squares? No. So this is where we want to ask ourselves a question before we say like absolutely no. Is there a GCF we can take out? So is there something in common that we can take out between 24g squared and negative 6? What can we take out? We can take out a 6. So if we take out a 6 and we look at what we now have in the parentheses, now they are perfect squares. Because 4g squared is a perfect square. 1 is a perfect square.
Sorry, she was like.
So we are going to go ahead and do our double bubble. What's the square root of 4g squared? 2g. And what's the square root of 1? A plus and a minus. All of this together, including that 6 on the outside, is part of your answer. So you could have some on your assignment where you just have to take out a GCF first, and then what's left will be a perfect square. So before you absolutely say no, check for a GCF.
Would it be divided by -6?
No, because we didn't change the sign here. It's still a minus.
Oh.
We want it to be a minus, otherwise we won't have a difference in our squares.
Wait, so the answer is 6 2g plus 1?
2 times 2g minus 1. Mhm. And again, what's another common thing is that we stop here. If you stop there, you'll get some points, you just won't get them all. Okay, because we're going to be doing what's called fully factoring, which means we have to take it as far as it can go. Okay, what about the last one here? Are those perfect squares? 27 and 12? No. But is there a GCF? So what can we divide both of these by?
3.
By 3. So we're going to take out a 3. 9w squared minus 4 is what's left in parentheses perfect squares. Yeah. So what's the square root of 9w squared? 3w. And the square root of 4? So 2 and 2, a plus and a minus. All of that together is our answer. Robert.
What if they're in the parentheses and they're still not perfect squares?
Then you're done.
Okay.
So let's say it would be kind of like number 3 on last night's assignment. We had 72x squared minus 63. All they had was a 9, and what was left was x squared minus 7, neither of which are perfect, so we're done. That means all we had was a GCF. Yes.
What about the numbers like 4 and 9? Since they're addition.
Well, can we do this pattern if it's addition? Then you can't do it. So you would just look for a GCF, and if there isn't one, just write not factorable. Any other questions at this point on the difference of squares pattern? Okay.